In this lecture, we're going to talk about a new terminology, which is the zero-sum games. A game is zero-sum when the sum of the payoff is zero. So what this means is we are playing in a closed system. So a zero-sum game is like a game in a closed system. So if someone wins, then someone has to lose. So this is kind of like gambling or kind of like a stock market. If someone gains, then someone else has to lose. And if you think about it, most games that we have talked about in the past, so this is the game from the last lecture, these guys are all zero-sum games. So if someone wins, if someone gains, then someone else has to lose. If Alice wins, then Bob has to pay, or if Bob wins, then Alice has to be the one who pay. Now, if you look at these zero-sum games, you can kind of notice how when we write it as a vector, it's kind of redundant anyway, because if we know that it is a zero-sum game, if Alice loses, then Bob is going to win, and then if Alice wins, then Bob is going to be the one who loses. So instead of writing this as a vector, I can kind of save time a little bit. So let me kind of redraw the my table here. So instead of writing a vector -1 and 1, I'm just gonna write out a list payoff here. So I'm just gonna write the first number that I see, and then we will understand that the number that we see in the new table, this is gonna be just a list payoff. So this is gonna be -1, -1, 3, 3, and then 3, -1, 3, -1. So now for a zero-sum game, when I see -1, I knew that this means Alice is gonna pay Bob $1, and then when I see 3, I knew that this means Alice will get $3 from Bob. And this works for two-person zero-sum game. So basically, the payoff for two-person zero-sum game are usually written using the first player's payoff. So let's take a look at the first example that we have here. So let's say we have so Alice is gonna be the first player here, and she's gonna be choosing the row, and Bob is gonna be the second player here, and he's gonna be choosing the column. Maybe I should make Alice pink and then make Bob blue. Okay. Yeah, so Alice is gonna be choosing the row, and Bob is gonna be choosing the column. So now let's put ourselves in Alice's shoes for a moment. So which choice should Alice choose? And it's kind of not hard to see that if Alice chooses the top row, then she'll either get $1 or $2. But if she chooses the bottom row, then she'll get either $3 or $4. So the worst case of the bottom row is already better than the best case of the top row. So this kind of means if we were Alice, there's no reason for us to choose the top row because the bottom row is already so much better. But we can analyze it this way as well. So if we put ourselves in Alice's shoes, and then we think about what Bob is going to do, and we see that if Bob chooses the first column here, if Bob chooses the first column, I kind of see that, well, if Bob chooses the first column, I should choose the bottom row, because 3 is better than 1. On the other hand, if Bob chooses the second column, then 4 is better than 2. So no matter what Bob does, it's always going to be better to choose the bottom row. So in this case, we will say that the bottom row dominates the top row, or the strategy S2 dominates strategy S1. So for Alice, S2 dominates S1. And this is how Alice should play the game. Now let's put ourselves in Bob's shoes. Let's see what should Bob do. Now when we look at this number, one thing that we have to remind ourselves of is that this number, well, it represents the so let me rewrite that. It's actually just a shorthand of the vector. So we have we have 1 and -1 here. And then we have 2 and -2 here. 3 and -3 here, and then 4 and -4 here. So the number that we see here, this is Alice payoff. So if Alice gains $3, that means it is Bob who has to pay Alice $3. So obviously Alice would like the game to end in a larger number. Alice like large numbers. So let me actually write that here. Alice prefer large number. number. And maybe I should also emphasize that this is only for the zero-sum game. So because it is only for zero-sum games that we can kind of shorthand this vector path into just a single number. So let me actually write this in different colors. Okay. So Alice would prefer large number because that would mean she would get that much money. On the other hand, Bob would prefer smaller. Or even negative is better number. We don't really see that here, but we can kind of see in the second example here. Bob would prefer the negative 3 here because this would mean Alice lose $3 and Bob has gained $3 from Alice. On the other hand, this number 3 here, this means Bob has to pay Alice $3. So Bob would prefer smaller number, the smaller the better. If it is negative, then it is even better. And I talk about the number in this shorthand table, not in this table, because this means Bob lose $1, $2, $3, $4. Bob lose $1, $2, $3, $4. Okay, so let's put ourselves in Bob's shoes and see what he can do. So Bob can reason like this. Bob see that, well, if Alice choose S1, so let's suppose for the moment that Alice is gonna choose the top row. What should Bob do? Well, Bob see that losing $1 is better than losing $2. So Bob's reasoning is that I should choose the first column. On the other hand, if Alice choose the bottom row, Bob can see the bottom row and see that, well, losing $3 is better than losing $4. So that means no matter what Alice does, Bob should always choose T1. So for Bob, that means T1 dominates T2. And we can kind of see how this game will play out already. Alice can see that, well, playing S2 is always better than S1. So Alice is going to play S2. So Alice will choose this second row. And Bob can reason himself and see that, well, playing the first column is going to always be better than playing the second column. So for Bob, he is always going to play the first column here. So if Alice chooses S2 and Bob chooses T1, then the game will end up at this payoff here. So Bob will pay Alice $3. So let me kind of go back to the theory here a little bit. So when I say some strategy dominates some strategy, that means the first guy. So if S dominates S prime, that means it's kind of like what we see here. It just means that S is better than S prime in almost all the cases. So there can be some case when they are equal. We're gonna see that in a moment. But there should be at least one outcome where S is better than S prime. And then we also have this principle of dominance, which says that dominates the strategy. So we should play strategy that are better. So it's something like this. So let's look at the second example here. Now, if we put ourselves in Alice's shoes, okay, let's see. Well, Alice can reason herself like this. If Bob play the first column, then Alice should play the top row. Because 1 is better than negative 3, getting $1 is better than paying $3. But if Bob choose T2, then Alice should also choose the top row. Getting $2 is better than getting nothing. But if Bob choose the third column, then this time Alice should play S2 because getting $5 is better than getting $3. So we can kind of see that, well, for now, we can't really decide what should we choose because, well, it depends on what Bob does. Sometimes I should choose the top row, sometimes I should choose the bottom row. So for Alice at the moment, well, we can't really say what she's gonna do. So let's put ourselves in Bob's shoes instead. Now, we can kind of see that for Bob, T2 is gonna be better than T3, and that's because, let's see, if Alice choose the first row, then T2 is gonna be better than T3 because paying $2 is better than paying $3. On the other hand, if Alice chooses bottom row, then T2 is still better than T3 because paying nothing is better than paying $5. So we can say that T2 dominates T3. So then this means for Bob, we can already eliminate T3. But it doesn't stop here. It turns out that T1 also dominates T2. T1 dominates T2. So for example, let me actually put myself here. So if Alice plays top row, we can kind of see that, well, playing T1 is going to be better than paying T2 because paying $1 is better than paying $2. And if Alice play the bottom row, then -3 here, that means Alice now has to pay Bob $3. So getting $3 is better than getting nothing. So no matter what Alice does, playing T1 is always better than playing T2. So for Bob, we can reason ourselves that, well, no matter what Alice does, paying T1 is better than T2 and T2 is better than T3. So we can eliminate these two options here. And then I can kind of say that for Bob, the best thing that he can do is to choose the T1. Now then, because Alice is smart and she knows that Bob is also smart, so she can reason ourselves that, well, I knew that Bob is smart, so he's not gonna pick T2, he's not gonna pick T3, he's gonna pick T1. So Alice can reason herself that, well, if Bob picks T1, then it is the better option for her to pick S1 because for now, getting $1 is obviously better than paying $3. So that means Alice can now eliminate the S2. So this game will end with Alice playing S1 and Bob playing T1, and Bob will have to pay Alice $1. Now let's take a look at the last one. Now let's put ourselves in Alice's shoes first again. So Alice can see that, well, if Bob plays T1, then it's all the same. If Bob plays T1, then she has to play Bob $1 no matter what she did. So she can't really decide. If Bob plays T2 on the other hand, well, she should play, let's see. If Bob plays T2, then she should play the last one because that means she will get $10 from Bob, and that is the better option for her. On the other hand, if Bob plays the last one, then she changed her mind. She should play the top row instead because that means she will get $3 from Bob. So for now, Alice can't really decide what she's gonna play, and if we look at from the entries by entries, we can see that the S1 does not dominate S2, so they don't dominate each other. S2 and S3, they don't dominate each other, and then S1 and S3 does not dominate each other. So for now, I can't really decide for Alice, she can't really decide how she should pick which of the three options here. So let's instead put ourselves in the Bob's shoes first. Now, for Bob, he can kind of see that playing T1 is gonna be a better choice than paying T3, no matter what Alice does. Because, well, if I compare, let's compare T1 to T3. I'm gonna put T3 in the purple here. So blue column is better than purple column, no matter what Alice does. Let's see if that makes sense. If Alice choose the top row, then choosing T1 will get Bob $1. So getting $1 is better than paying $3. And then if Alice choose the middle row, getting $1 is better than paying $2. And if Alice choose the bottom row, then getting $1 is better than paying $1. So we can kind of see that T1 dominates T3, so we can now eliminate T3. But now T1 and T2 doesn't dominate each other, so for Bob, we can only eliminate one thing. So now let's put ourselves back into Alice's shoes. So now, because again, Alice is smart and she knows that Bob is smart, so she knows that Bob is not gonna play T3 for sure. So she can use that knowledge to eliminate some of the choice that she has. So sometimes when we think about the how strategy dominate each other, we may have to think iteratively, like what we are doing here. So once Alice knew that Bob is not gonna play the last column, she can compare the choice that he has left and she has left and see that the bottom row for her is gonna be the best thing that she can do, because, well, if a Bob choose the first column, well, then she doesn't really care anyway, because she's gonna have to pay Bob $1 no matter what Bob did. And if Bob choose T2, we can see how S3, this is the better option. So S3, we can say that S3 dominate both S1 and S2. So because having -1 is better than -1, and well, it's kind of as good as -1 that we have in the other two options. So this is kind of what we have said earlier. When one strategy dominates another strategy, then it has to be as good as the other option, and then there's gonna be one outcome which is strictly better. So that can be equal in some entries, but for at least one entry, it has to be strictly better. So we can see that for a list, S3 is gonna dominate S1. -1 is the same as, -1 is the same as -1, and 10 is better than -10, and then -1 is better than -1, and 10 is better than 0. So a list can now eliminate S1 and S2. So that means a list is going to play S3 for sure. Now, if we put ourselves back in the Bob's shoes, well, Bob can then reason herself that, well, because I'm not gonna play T3, so then Alice is not gonna play S1 and S2, so Alice is gonna play S3. Now, if I have to choose between paying $10 and getting $1 from Alice, I'm just gonna choose the first one, so I'd rather get $1. So this is how Alice and Bob should play the last game that we have here.